So we've been talking about sensitive information, including things like passwords and dealing with that. Now we're going to, this time we're going to focus more on users, the human problem, dealing with access control and issues around that access control and access management. So, any company generally has a bunch of resources, information systems they want to protect, and information systems such as servers, workstations, applications, and then users, of course, need to use those workstations and need typically these days have a bunch of mobile devices, personal devices that they often want to use at the company presence or remotely for work purposes, possibly along with personal purposes as well. And of course, this dealing with these personal devices is a perennial problem for companies. Different companies have different, policies regarding personal devices and things like that. Some companies say, well, for business, you have to use this company-purchased device, not your own personal one. Others have, many others, have a so-called BYOD, bring your own device policy. Which tends to be a lot more acceptable. That's usually people don't like to carry around two devices and prefer just to have one of their own choice. But that has security implications too that administrators have to think about. So you've seen versions of this diagram before. At least a simplified illustration of kind of a standard network, corporate network architecture with, say, a main office here with two levels of firewall with a demilitarized zone or DMZ between, which again contains the special servers that need to be accessible from both outside and inside the network. Things like the VPN server, the public-facing web server, email server, things like that. Kind of have to be in the DMZ, whereas the things behind the servers and user devices behind the second firewall are normally, not directly accessible from outside, and you try to keep them under fairly heavy lockdown. And of course, and then you often have other offices elsewhere, and then you need to link them together across long distances, and various forms of virtual private networks and encrypted interoffice links are kind of standard practice for linking those together. But of course, this creates a complicated picture, and sometimes complicated enough that it might sometimes seem like Wonderland or something, with many different players with many different interests and requirements. Both users, employees working from within the office, employees working remotely, customers who need to access electronic services, or business partners that need some form of access to the network and its services. Different offices in different locations, and so on, right? And the unfortunately, kind of the natural situation is, in many of these cases, is it's easy for one weak link, one security mix-up to potentially give an attacker, a way through the defenses. And so, just like in the weakest link game show, except you don't, in real information security, you don't usually get to vote at on who the weakest link is. You just discover it once the attack incident has actually happened. So that's kind of that. We'll be talking about various issues that feed into this from the user perspective. How do you manage users across these big complicated networks in practice? And so we'll talk about a number of the standard practices, in particular related to access control, authentication. So we just talked about password-based authentication, but that was kind of the password, focusing on the password storage and the information protection. Now we'll focus on how users relate to passwords and best practices regarding them. And then we'll get a little deeper, a little lower level, and look at how in today's most widely deployed networks, how access control for network-wide access control is typically managed in most networks, especially corporate networks. Improvements like multi-factor authentication and user training and stuff. So, okay. So let's first look at access control, kind of standard approaches, kind of the way access control works and basic concepts. So access control, is a very diverse topic and has a long history. Goes back a long way, but in the research literature, and there's a lot of research literature on access control, kind of developing the theory of access control, generally the objective is to define some kind of matrix, basically a binary matrix in which, say, the rows of the matrix are subjects, users, processes, some entity that, needs to access objects, and then the columns represent the objects, the things that, users or subjects might need to access, right? And fundamentally, the access matrix says, for each cell in that matrix, for each combination of subject and target, does that user have should that user or process have access to that target object? So, kind of the oversimplified theoretically view, all access control is just a matrix. Matching subjects and targets and saying yes or no whether this subject is supposed to be able to access that target in some particular way. And of course, you can have several of those matrices, and often do, one for each operation, such as read, write, append. There can be multiple different types of access too. Now, of course, we've brought up the principle of least privilege already. That's kind of a pervasive principle throughout security, and we need to think about how to achieve the principle of least privilege when we're dealing with access control mechanisms. But also more generally, in any situation where there's many users and many potential target objects, often millions of potential files or database objects or database tables and rows that you ultimately have to make access control decisions over. The number of users, number of objects explodes. This becomes a n by m matrix. It's just completely impractical to administer the whole matrix as one giant sheet. And so this has led to the need to create access control abstractions that are higher level, that allow administrators to reason at a higher level, what groups of users should get access to what groups of objects, rather than just kind of an individual pair level. And so we'll look at several common abstractions for defining those matrices in more manageable ways. So now, just to review on another important point that has come up before, but worth reiterating, access control comes into play at multiple levels in the system, and in multiple ways. So we've got network level access control, the access control that determines whether a given one machine is able to connect to another machine at all. And the firewall configurations and stuff generally manage that. Then there's user management, whether a particular user is able to authenticate and log into a particular service connect to a particular network drive, connect to, log into a particular web-based service or cloud service or whatever. Then there's operating system access control, the usernames and passwords in Unix systems. And then application level access control, which might be, implemented by the database engine or HTTP level or, different things like that. So again, just keep all those in mind. Now let's look at the typical access control abstractions that have become standard ways to allow administrators to more scalably manage these giant matrices of subject-object rules. And so we'll look at three common paradigms: role-based access control, discretionary access control, and mandatory access control. In a way, these are a little bit out of order because discretionary access control is kind of, often the most basic starting point, but role-based access control, in some sense, maybe more intuitive. So we'll start with that. So role-based access control is a concept that, again, some more security best practice standards from NIST, for example, and probably from other standards organizations have addressed. And basically, the concept here is you achieve scalability of the management problem by not making access control decisions at an individual user granularity, but you say sort users into roles, and then you make access control decisions, direct access control decisions based on roles. So you might have different roles for different type of data objects, such as owner or a email forum or something like that, such as owner, moderator, collaborator, reviewer, and viewer, someone who can only read but not edit anything, right? And for each of those roles, there's going to be a set of permissions that role is associated with. So you define a small matrix with just roles as the rows. Excuse me, the difficult. And then particular permissions. This role can do this operation and can't do something else. Like, everybody can navigate pages, even just viewers, but only owners and moderators can modify the permission controls and stuff like that, right? And how this kind of matrix is set up is totally application dependent, but it's a general paradigm. And then you associate groups of users that then in a separate step, the administrator says, okay, for user Alice, well, Alice has role owner, and Bob has a different role. Sometimes users can be given multiple roles. Sometimes users can play multiple roles, which means they have the access of each of the roles. And so that just kind of reduces the number of decisions per user, because that way you no longer have to reason about what permissions a particular user has. You only reason about what roles a given user plays, and then let the permissions come, kind of be abstracted and come automatically from the smaller role charts. Right? And so all of these roles and the division of users into roles and what permissions those represent is the critical part of the access management. And various standard network security and OS security tools, very commonly the Windows standard Windows authentication tools tend to support these things. We don't need to get into all the details, but let's just look at the advantages and disadvantages of this general approach. So in many ways, and an advantage is that it's fairly intuitive. Often users do, play a natural role. They're, in companies, users often have titles, positions. This is, kind of a direct organizational reflection of what their role is supposed to be. So sometimes it can be intuitive and easy to assign users to roles. But it's not always really easy in practice because sometimes users play more ad hoc roles. Sometimes the roles are more fuzzy. So another advantage is when a user changes a role, or when you want to change permissions, you can change the permissions, say, for an object or for a role in one place and have all of the users in that role automatically be affected all at once. So, you don't have to go and track down individually all of the users that should be affected by this access control policy change or something. So there's some clear advantages. There's also disadvantages. Sometimes it's, it can actually be kind of difficult to figure out what the roles should be, what roles actually make sense in this application and company context. And, you might not find out that they don't really make sense until, some users start complaining that, hey, we've already always done this thing, but suddenly you revoked access to that we needed to do that. And then, kind of you discover that people were playing hidden roles that weren't really, on the explicit map, and then, have to adjust for them, have to hack around them. And so the meanings are fuzzy, and sometimes it's this can create interesting challenges. Another issue is if you sometimes you have different the same kind of roles that apply to multiple different departments, but you then have to ask the security question: should we have one role for everybody across the company that plays, this kind of function, or should we have a different version of the role for each department, that has that role? So a sales representative role or something like that. Do you have a sales just one sales representative role across the entire company? Which might be a security risk if the sales rep role over here can, access, really secret information about just new unannounced projects over in that other branch that's completely unrelated. That could be a, major least privilege failure if you do that. Whereas if, the other obvious alternative is to have a role for each product line or each, kind of division of the company, which, gets things better into least privilege, but creates a lot more roles to manage, right? And so these are, there's always those granularity trade-offs and things like that. So just some of the issues there. Now, so the second general approach, discretionary access control. This is often kind of the default because it's what practically all Unix-based systems come with at an operating system level. The basic idea there is just to let the owner of whoever created the file or created the database object, the owner decides who should have access to this, and under what conditions, what kind of permissions. So that's what it's meant by discretionary. Whoever owns it has the discretion to decide how to share it, right? And many cloud-based systems like Google Drive, file sharing systems basically use discretionary access control. Where you create something or upload something, and then there's a way you can say, okay, I want to share it with these people. Add these permissions, revoke those permissions, stuff like that. That's all discretionary access control in effect. Now, so once again, back to the scalability problem. we've got to, ultimately these access permissions are a matrix, subject-object matrix, but there's different ways to actually represent that matrix, even in the case of discretionary access control. And the two common ways to do that are either, the two obvious choices are we could break down the matrix by, focus on the columns, or we could focus on the rows. So when we focus on the columns, we take a whole column representing all the users who do or don't have permission to access a particular object. We bundle up, all the information about a column together and store it with the target object that we're talking about. So this is called an access control list. So we say, we have a file in the Unix file system, and the file has certain permissions. A user, a group, more sophisticated file system extensions that are available both on Mac and on Windows machines often support, not just user and group, but additional, you can add list multiple users and, that have access to a file and edit the permissions each has. And so that's basically taking a column of information and attaching it to the target object whose permissions we want to control, right? So the other, and this tends to be the most common, most familiar way that these kinds of systems work. The contrasting approach is to take a row-oriented approach, where we say, okay, let's focus on a user, gather up all the things the user can do, all the targets, objects, and kind of special rights or capabilities the user has, and associate that list with the user, right? And so the administrator is, in the ACL thing, the administrator is going to be going and editing data associated with the target object, like a file or database row, whereas with the capability approach, the administrator is going to be focusing on, well, what can this user do, right? A list of things that the user can and can't do, right? So it's, ultimately we're representing the same information, but taking a different perspective. And in practice, systems, both capability-based and ACL-based systems have been built, and in fact, elements of capabilities and accesses are very pervasively present in common systems we use, including Linux systems. And often there's some, even though we're ultimately representing the same information, basically experience has shown there are often kind of different trade-offs, positives and negatives, of each of these approaches. For example, with ACLs, access control lists, if you want to revoke, access to a given object, if you care about an object, you want to revoke access or control or figure out who can access the object, you just look at the object. You just look at the access control list attached to that. You edit it to revoke, access if you want to. So that's easy. Whereas with a more capability approach, if you're interested in who has access to the object, you have to go search through the capability lists of all the users to figure out, okay, who actually has a capability to access that object or to do that thing, and so, so actually revocation or even census, coming up with a census of who can do what to this object is harder in the capability model. On the other hand, the capability approach can be more natural for some things. For example, in systems that you do a lot of delegation, where you say, okay, I want to give this user a capability to do, a certain thing, but that user or his program isn't going to do it directly. Instead, he's going to delegate that capability to a helper process or something, to a process that's, or another user even, that's specifically tasked with doing that. With a capability-based system, often there's a way to say, okay, a user, am going to delegate my capability to do this thing to this other object to this helper who's going to do it for me. Right? Whereas with an ACL-based system, if you want to do this delegation-based thing, but the process that's supposed to do the thing for me, to help me, is under a different user ID, then I have to go and edit all of the ACLs of all of the files that might be affected by this now delegation-based activity, and that can get complicated, right? So these are just a couple examples of some of the kind of administrative trade-offs between these different approaches. And I think it's still not it's still very much an open question. Is either of them the right or the wrong approach? In a given situation. Okay. So, but just to be aware of those kinds of issues. So, like I mentioned, Unix has discretionary access control built in. It's mostly ACL based, but modern Linux systems especially often have some level of capability based access control as well, especially when we're talking about administrative rights, special administrative access. It also has quite complicated, and often traditionally error-prone methods of handling, root privileges, special privileges. For example, the set UID, set GID bit, which allows you to say mark a file that says, anybody who runs this particular program. Anybody can run the program, but then the program will get elevated privilege and will run as root, or will run as a particular user rather than as the user who calls it. And this type of mechanism was created for very good reason. We needed, we typically need to store password databases and other kind of sensitive information, and we don't want those databases to be accessible to just anyone on the system. But we want anybody to be able to log on or to change to a different user if you know the password for that user. And so we have set UID programs that are responsible for actually managing the logon process, right? And that set UID program needs to be able to get to these special files like user bin password that only root can access. But that makes that executable basically part of the trusted computing base. If it's buggy or exploitable in any way, then the system's security can be completely blown. And this kind of thing has happened over and over and over. Like a lot of very careful attention tends to be paid to kernel patches, kernel security, kernel level upgrades, and somewhat less for user level utilities such as the login daemon. But in practice, these are just as critical because they have these special privileges. Even if they're run as user space processes, they're just as security critical. And so that's often been a big problem in general system security. Okay. So just like role-based access control, discretionary access control has advantages and disadvantages. It's flexible and easy. It's fairly intuitive in a different way. Just let the owner decide who should have access. But a clear disadvantage, it relies on the resource owner's judgment. Especially in a corporate setting, individual people just making random decisions is not necessarily, individual people are not always reliably, knowledgeable about, the access, the higher level access policies that are supposed to be applied. And, if you rely on each person who creates a file or object to correctly set the access control list according to a policy that's posted in a memo somewhere that hopefully they read 3 years ago, mistakes are going to be made, right? And so, you know, kind of discretionary is not always, you know, especially for that kind of thing, discretionary decisions are very often not the right ones. They're not consistent with higher level policies. So the third category, mandatory access control, was created a long time ago, partly to try to tighten up security much further, and this is especially associated with military-grade security systems. So the classic origin of, you know, kind of the traditional theory and practice of mandatory access control comes from a famous book that's just tends to be called the Orange Book, from way back when. I can't remember when it first came out, from the U.S. Defense Department, but many other you know, countries in the EU and, you know, Canada and other countries have their versions of this now that define the handling of highly sensitive information, you know, information of national security importance and whatnot. And in this type of practice, the basic goal here is to handle access control in a non-discretionary way, namely labeling data and controlling access to data in such that even someone who does have legitimate access to it cannot, or at least cannot easily leak it in the wrong way, can't violate an access control policy. And so this is why the access control is said to be mandatory. You know, some so the typical way, so, you know, once once a particular document is labeled with a particular label, such as, you know, confidential, secret, top secret, so if a document is labeled secret, that's at a particular level in this labeling hierarchy, which the system then tries to enforce the property that only users with either secret or above clearance, namely secret or top secret clearance, can ever access that document. And further, even a user with secret clearance who actually can and is allowed to view that document cannot send the document or cut and paste it or, you know, do anything that would transmit that document to another user with only unclassified or confidential clearance, right? So that's the basic goal. You know, even if the user's compromised or coerced or deliberately misbehaving, you know, users with access to high you know, security information are not permitted to transmit that information to lower classification level users or to move information down the levels. Okay, so that's the basic goal. And, you know, again, there's a lot of kind of theory and practice that has developed around this over, you know, the past decades. In fact, so I mentioned the, you know, kind of the sensitivity labels that they typically use. So, you know, at least in the US, they tend to have these 4 levels, secret, unclassified, well, yeah, those 4 levels. This is a, so often we want to reason about not only the secrecy or, you know, how secret, how sensitive information is from a privacy or confidentiality perspective, but also how much we trust its integrity. How much do we trust the source of information? How confident are we that the information is accurate? Or, you know, how confident are we that the source of the information is trustworthy to produce that information? And so there's so you know, to handle that, we can actually attach both secrecy labels and integrity labels. And the integrity labels kind of have the opposite rule, where you know, where you can't move information from an untrusted category to a trusted category, but you can move information from a trusted category to an untrusted category. Yeah?
Like the table seems to give the idea that, so since we have secret, unclassified, trusted, and untrusted in the same headers, it seems to give the idea that those are like not orthogonal. So like the secret and classified are...
Yeah. So exactly. So I wasn't going to get into the details of this table. This is kind of a classic table presenting, that explores particular rules, according to a particular concept of how these trusted, untrusted, secret, unsecret, unclassified things might work together in a particular historical system. I can't remember, which system this was, but so. But in general, we're talking about if a process creates a new file, but the process is in the untrusted category, what other processes are then allowed to read and depend on that information? So if an untrusted process, let's see. Yeah, I would have to go back and study, carefully study the table to interpret properly, kind of what all the cells were intended to mean. But it's and there's nothing that fundamentally says this is the right table. That's just kind of the gist of what it's trying to get to. In a system where many processes can read secret, more or less trusted information, more or less secret information, and produce information. The goal is to track these information flows around and prevent processes from transmitting or moving information in ways that violate these rules that say secret information, information only moves up the secrecy ladder and only moves down the trustworthiness or integrity ladder, right? So that's the general gist, and if you study this table closely, I think you can kind of figure out what the authors were getting at, even though there's no reason it's perfect or the ultimate set of rules. Just an illustration. Okay. Yeah. Okay. So again, these are just examples, but the gist is to create a set of rules that even authorized users can't violate and can try to prevent information leaks. For decades, in fact, Mac was basically never used out of defense level security systems, military grade security systems, until a form of Mac was introduced into Linux in the form of Linux security modules, or LSM. And this basically is a somewhat flexible, programmable mechanism that makes it possible to implement Mac policies. Oh yeah, and by the way, I want to emphasize this kind of Mac is completely different and completely unrelated from the message authentication codes that we talk about in crypto that uses exactly the same acronym. So please don't be confused about those two completely conflicting and conceptually completely unrelated uses of that acronym. So LSM, Linux security modules, added basically a programmable way to establish either discretionary or especially mandatory access policies by allowing you to implement a reference monitor as a Linux module, where when this is in use, anytime any application process tries to call a given system call or try to access a particular object, it's going to, within the kernel, it's going to invoke this reference monitor and just ask this reference monitor, is that allowed? Is it not allowed? And here's the information of, what the decision needs to be made. And so this is a fairly general general purpose mechanism. It can be used to enforce a wide variety of policies. And it has been used in a lot of different ways, some more, some less, like traditionary military style MAC. And so, so you have, basically the kernel is using the reference monitor, to make access control decisions at all of these sensitive points, such as system calls. And then the reference monitor is supposed to be kind of the centralized decision-making brain deciding, whether any given access is allowed or not. And in this case, the way that these decisions are made and the reference information it uses, the organization and format of that reference information is essentially programmable. And there's, again, many standard ways to do that. This has proven to be a useful tool for a lot of things. In hardened system deployments, for when you're trying to customize a kernel for a particular system and lock it down as much as you can to enforce principle of least privilege, this kind of thing can help ensure that even a compromised process would have a lot more difficulty allowing, if an attacker breaks into one process, like a potentially vulnerable login process or a web server, maybe you can prevent the attacker from from increasing his privilege or jumping into other processes. And so, again, it's just another often used as a tool to better implement least privilege, the principle of least privilege. Okay. So I won't get into all of the details there. But once again, like all other access control paradigms, it has pros and cons. So it does, in principle, achieve its key function of addressing some of the weaknesses of discretionary access control. The fact that, namely, the fact that discretionary decisions are not necessarily consistent with the policies they're supposed to be representing. It's very easy for mandatory access control systems to be too restrictive. So these are the kind of systems that users get mad about. You implement MAC, you can just expect a lot of complaints and pain until you figure out all of those things that users were used to doing and accustomed to exercising discretion, and now suddenly they need to call an administrator to get on with their lives and make progress. And so that's often a it can be just a much more administrative and intensive and high overhead, high user friction type process, right? And it's also not remotely perfectly secure because of side channels. We've talked about side channels already. We'll talk about side channels more. There's often other ways, if a particular process gets malware infected and wants to signal, secret or top secret data out to an unclassified process that's listening for it, it's well known that there are all kinds of ways, even if it can't just drop it in a file and allow the other process to read it, and it can't send a message to the other process, but maybe it can just consume a lot of CPU time and then go silent, and consume a lot of CPU time and go silent, and the other process just monitors the CPU usage and and listens for the smoke signals. So there's a bazillion different forms of smoke signals, in using a bazillion different types of covert timing channels. It is extremely difficult in practice to close those down in practically any realistic system. So it's arguably, it's arguable how much real, security, how much any MAC system is really succeeding in, fully addressing the vulnerabilities in discretionary systems. So, and again, it's, and is all of that additional pain we're imposing on users really worth the security benefit we're getting. So, okay, so that's access control. We'll try to go through the other more quickly. It's probably a good time to take a short break now.